So like I said, I'm Ralph Dawes, and I get to introduce our speaker, say a few words in advance. So welcome to the Quimper Geological Society lecture series, this October 14th. And I want to thank Leslie Rubal for getting us organized and coordinating all this complicated technology to make it work. According to Michael Machette, this is our 97th event as a geological society since we became a part of the Jefferson Land Trust. So we're getting toward the 100 there. Now looking ahead, we're now in our season of guest speakers that runs fall, winter, and once we get them set up, spring, but not in summer. Anyway, on November 11th, we're going to have David Williams and Liz Nesbitt here in Port Townsend to talk about their new book on the fossils of Washington. So that's exciting. And then after that, date and time to be announced, there will be a talk by David Brownell on drainage evolution of the Dungeness River. Okay, so that's coming up, and there'll be more after that, I think, once we get them arranged. So stay tuned. But let's get to tonight's talk. So here's my bio for John Oldow. Correct me if I make any mistakes, please. So he got his bachelor's in geology from the University of Washington. I won't give all the years, back in the day. PhD in geology from Northwestern University in 1978. And then he taught geological sciences with a specialty in structure and tectonics for 40 years, now retired. At Rice University for 17 years, University of Idaho for 13 years, and at the University of Texas at Dallas for 10 years before he retired in 2018. And he's from Anacortes originally. And so he returned home to the Pacific Northwest and lives on northern Whidbey Island now. Still active in research projects like the one he worked on recently with a grad student that he'll be talking about tonight in the Western Great Basin, northern Alaska and northwestern Canada, and the San Juan Islands of Washington State. And he continues to consult for mineral and petroleum exploration companies, or at least anyway, and holds a position. You hold a position at Western? Yeah, as a research associate at Western Washington University. Okay, having so quite a lot of background and expertise there. Not showing up on the camera, but that's okay. So anyways, please welcome John tonight. The title of his talk is Fidalgo Ophiolite Revisited.
So what I'm going to do is I'm going to talk about the primary motivation of what started this project, and part of the revision of the Fidalgo Ophiolite was an unintended consequence of our work. It was not one of our objectives. It's just the geology that led us to a different interpretation of the observations, because we started this project not particularly interested in the Fidalgo Ophiolite. I bought into the existence of the Fidalgo Ophiolite, but in the process of mapping out Fidalgo Island, we started to realize that there was something wrong with the story. So let's just move forward here. And there we go. So again, just a quick summary of who I am. I've been to a lot of different universities after I was at the UW. I went to Northwestern, then I went 2 years at TCU in Fort Worth, then Rice, University of Idaho, and then to our great surprise, I got dragged back into Texas for another tour of duty, and that's where I ended up retiring. And now I'm a research associate at Western Washington University, and my graduate student did a lot of this work, excuse me, particularly in the aspect is David Catapult. He got a degree at UT Dallas, PhD there, and he's a structure tectonics, spatial data analysis, and he's been a company in Dallas he's been doing quite well with. And he's helped out the old guy, me, and we started a joint venture where we're doing exploration. We're working in geothermal in the Great Basin. So we have our Walker Lane research partners, which include former graduate students. I supply sort of the geologic background and what's happening in there. And they do the really fancy analysis, doing things like machine learning and some of the most sophisticated things you've seen. But it's been a really Okay, so what we're going to talk about is what the objectives of the project are, what led us to working on this. So the first part is for a long time, we were here to test the hypothesis of what there's been, for my entire career, a big controversy about which was the sense of displacement, sinistral, dextral, both, what was happening in terms of movement, and most importantly, large-scale arguments about how far things slid along the coast. And so that was the motivation we had, because from the work that was primarily done by Ned Brown and the people from Western Washington University, they had an existing model that said that the Cascade naps linked structurally all the way on Long Island group. And as I will show in the next slide or two, that creates a real problem because that's the places where you could have a mobile latitudinal shift displacement. And so it was a locking point. So if it's true that the San Juan Islands and the Northern Cascades are in fact one and the same, then you can't bring displacement through that boundary. So that was our primary objective. And the way we actually addressed that is we were interested in looking at the timing and the kinematics of the emplacement of the San Juan thrust system, how it relates to the Rangelia terrane, which is Vancouver Island, and how all of these structures relate to the structures of the North Cascade naps. And so it's all based on geologic mapping, lithostratigraphic, and structural analysis. That's the kind of things that we normally do. And so we mapped macroscopic relationships. So we remapped most all of these islands. And so we wanted to be able to use faults and folds as form surfaces, work out the sequence of events in the deformation of this region, and then characterize the structures of superposed deformation and figure out the sequence of events, the imbrication, and the deformational history. Okay, so give you the results and conclusions first of all. First, and we can demonstrate, as I'll go through and explain how, that the fold and thrusts were imbricated during the Cretaceous to Eocene during imbrication and attachment to this part of North America. The big news in terms of the bigger hypothesis that we're testing is that the rocks of the San Juan Islands and the Eastern Sailor Sea and the North Cascades are discrete and different. There are no possibility that they're the same rocks. And put this into context, this is exactly the conclusion that Peter Misch came up with in 1966 in one of the extremely rare publications that he actually put out, that he says the biggest boundary between the San Juan Islands, Vancouver Island, and the Cascades is Rosario Strait. So that's in his 1966 paper. And the point is he's spot on. I mean, short, jump a little bit ahead. East of Rosario, we have a lot of structural bodies that are imbricated. We have a lot of peridotites to the east in a belt that ranges from almost the Canadian border all the way into west of Rosario Strait, all the way into Alaska, no peridotites. So it's a big boundary that runs through that boundary. Okay, so what we can say conclusively is the imbrication of the San Juan Islands and southern Vancouver Island, which is the Rangelia terrane, occurred in the Paleocene. And it amalgamated this assemblage as a block in the Paleocene, and it was translated along the coast to its present-day location where it was actually locked in place by the late Eocene. So those are the sort of take-home aspects. Now, here's the unanticipated result of this study, is the fact that the Fidalgo Ophiolite, which is the Decatur terrane, is not an intact sheet of arc continent mantle rocks. Rather, it's a volcanic sedimentary melange containing blocks derived from an ophiolite. And some of these blocks range in scale from anywhere from centimeters all the way up to kilometers in scale. And so what my objective here is first to show you why we worked here, and then follow it up with a sort of a guide through what we call the Vindovi assembly, used to be the Fidalgo Ophiolite, to show you why we made the call that this is not an intact succession. Okay, so what's up? but I can't go too far. Okay. Okay, so if we look at the continental margin, and this is a little awkward, whoops. We can see that America all the way down from Alaska through the Canadian Cordillera into the Western US Cordillera can be subdivided into three major belts. White is the cratonal part of North America, that's unequivocally North America, shown in the this color is rocks that have been displaced and deformed, but they're definitely part of the Laurentian continental margin. So they're not exotic. They're from around here. Farther to the west, in this green and blue, is peri-Laurentian rocks, which means they are probably associated with different parts of the Laurentian margin, the old continental margin, but they've been slipped around quite a bit. Now, one of the things that really to pick up on right here is the profound difference in the geometry. Crossing this boundary right through here and how everything changes when you get to the Western Great Basin in California. Very different system of structures. And finally, the shown here in purple, the outboard, the purple things like Alexander, Rangelia, these other exotic terranes, these didn't come from here. These are the rocks that were actually brought in and during a complicated system of migration and accretion to the continental margin. So what we're interested in is working out the controversy that has been in play for, again, most of my career. It's the magnitude and timing of both sinistral and dextral transpression. Sometimes the terranes were moving south, sometimes the terranes were moving north, and the problem is there's no question that they're moving. We've even found many of the structures on which all this displacement occurred. The problem is how much did they move and where are those specific boundaries, particularly at the transition from British Columbia into Oregon. And so the big question is, what was the history of displacement between 120 and about 85 million years ago? And the various arguments is there's been anywhere from 1,000 to 4,000 kilometers of latitudinal shift on these different parts of these terrains. So the whole estimate of magnitudes is based on paleomagnetic data, paleontological correlations between the terrains and rocks that are in place on continental North America, and on geological reconstruction. So the big question of latitudinal shifting and migration of these terrains is localized along this boundary between the exotic terrains and the rocks that are the peri-Laurentian margin rocks. And so the most recent piece of work that's come out in about 2 months ago, I think in Tectonics or Lithosphere, is George Garrels and his students from the University of Arizona have been able to document a left lateral shear zone that they've now mapped over 600 kilometers along strike. That originally they said it was early Cretaceous, and new dates that have just come out now say that it started in the late Jurassic. So we've got a major left lateral displacement. And now since about 85 million years ago, everything has been right lateral. So one of the real complicating factors here is things went south and then they went back north, and the magnitudes of north and south displacement aren't the same. And sometimes they drop little pieces off in the wrong place. So it gets to be an extremely complicated boundary. So one of the problems is we've got these really, we've got these really well-defined belts and well-defined deformational belts here, but as you get down south in the vicinity of just east of Vancouver Island, a lot of the boundaries are underwater. And so you get juxtaposition of rocks across narrow stretches of water, but you can't look at the actual structures. And so what is particularly important here is the southern continuation of this boundary goes down through the San Juan Island and Northwest Cascades. nap complex. And so these structures, this tie across this boundary is critical because it crosses over the projection of that boundary to the south. And so the question is, how well established is that correlation of the rocks in the San Juan Islands to the North Cascades? So here's, let's see, make sure I get, no, there. So here's where we would attribute a major fault system that separates clear Rangalia. This is the coastal plutonic complex. There's not much in the way of non-igneous rocks in this area. These are definitely paralaurentian terranes. We have a boundary that we can find here by juxtaposition of age equivalent rocks. On the east side, they're upper amphibole metamorphic tectonites. On the west side of Tectonic Island, they're sedimentary rocks. So they are relatives, but one set of rocks went to the bowels of the earth and came back, and the other one stayed at the surface. So here's the big problem right here, is this call that right across this boundary, we've got this correlation of the naps of the Cascades into the San Juan Islands. So we're going to go to that. So this idea has been in place since about 1975. So we can look at Joe Vance thought there were correlations between the rocks that we have in the Cascades out into the San Juans. And this set of geometry and structures was Vance, Wetton, Brandon, et al. For about a decade. This is the idea that there's a correlation of these structures across this boundary. Later, Brown and Garrels and Ned Brown at Western extended some of these boundaries, rearranged the boundaries, but again, the whole point was that there was a continuation of these structures from the Cascades all the way out into the San Juans, and that the big boundary was between Rangalia and the San Juan Islands. Okay, so this is where I'm going to simply tell you, this is the most recent compilation that we have of the various geologic components of the, oh, sorry about that. There we go. Recent compilation. So we have Jurassic or Cretaceous Nanaimo group, Rangalia, the San Juan Islands, two different packages, the so-called Decatur terrane area of Fidalgo, Cypress Island to the east, and then all the structure sheets that we have in the Cascades. This is a compilation of our work, and what it simply says is that we have different rocks in different belts that are separated by either thrust faults or large-scale steep, probably strike slip faults. So what I'm going to do is one of the important points, given the fact that these rocks are so complexly deformed, is if you can work out the superposition of structures, you see one fabric crossing another, you can work out this is first, this is second, this is third, and so forth. And we can do that through 4 deformations. But the big problem we have is that we need to try to establish the age of those deformations, and you can't do that from the fabrics themselves. But the good news for us is that we have rocks of different ages that have different structural histories. In other words, old rocks have all 4 generations of structures. Intermediate ages have 3 of the structures, and the youngest rocks have 1. And we know that the ages of these rocks so that we can actually put time brackets on when these deformations occur. So let me back up here. So what I'm going to show next is we're going to go up into this area. This is the Gulf Islands and parts of the archipelago north of Orcas Island to take a look at the Nanaimo formation and the deformation these rocks have experienced. It's important because these rocks are late Cretaceous and they have 3 generations of structures, whereas the rocks that are older and thrust over the top of them have 4 generations of structures. And as we see, ultimately, the youngest rocks, which are here, the Chuckanut Formation, which is Eocene, has 1 generation of structures. So we can actually date the ages of these structures, and everything occurred from Cretaceous through the Eocene in a sequential development.
your audience can't see that red pointer. So
You can't see that. Oh, of course they can't see it. Oh, yeah. Well, I'm not gonna try to,
so
okay.
what to look, like work is fine, blah, blah, blah.
I could run a mouse, but then I'd have to run both hands simultaneously. And I think that's a bridge too far. Okay, so what we're gonna talk about now are all of the islands, the Gulf Islands, Susha Island, all the ones in green, various shades of green and orange that are thrust over by the San Juan Islands and parts of Vancouver Island to make a thrust belt in this region. So the first deformation in these areas are west-northwest trending folds that are found all through Canada and into the western part of the US. And I'm sorry, north of Susha, but you can do this. I don't do this. So we have the west-northwest trending folds running through here. These are involving rocks that are late Cretaceous. As you go from west to east, these rocks have a major angular unconformity where it cuts out over 1.5 kilometers a section as you approach the mainland. Superposed on these structures are northeast trending structures that refold the pre-existing folds and faults. So we can actually work out from mapping out the big structures that there are 2 generations of structures that have happened since the deposition of the Nanaimo group. So this deformation would be Paleocene. And then finally, if we look at the deformation, 1 generation of structures, there's another generation of west-northwest trending folds, the single deformation that is found in the Chuckanut Formation. So if you're in the Chuckanut, you have 1 deformation. If you're in the Nanaimo, the late Cretaceous rock, you have 2 deformations. And if you step all the way down into the basement rocks, shown here in gray, or in the thrust sheets of the San Juan Islands, you've got 4 generations. And so we can broadly date these deformations, and then using the geometry and strain analysis of these structures, we can say which way these sheets move through time and when they actually immigrated one to themselves. Okay, back here. There we go. So Peter Mish picked out this dark line, the north-south line through Rosario Strait, as the primary boundary between the rocks in the Cascades to the east and in terms of the San Juan Islands to the west. Work by the Jim Mueller from the Geological Survey of Canada argued that many of the rocks in the western part of the San Juan Islands are part of the basement of Wrangellia. And so that was work that was published in the 1970s. So he came at it and saying, well, if I go to the western parts of the San Juan Islands, I feel really at home. This looks like the Sicker group. And Peter Mish, coming from the Cascades, came all the way down and said, well, okay, things are about right, but for sure at Rosario Strait, there's a big break. And so we agree with that. So we've done a lot of work in the Western San Juans, the Gulf Islands, and even in parts of Vancouver Island to work up the sequence of history of structures. What the objective of the study that I'm presenting today is to look at those structures in the area east of Rosario Strait on Fidalgo Island, Cypress Island, and the smaller islands all the way up toward Lomi, the islands of the Eastern Salish Sea. They're strictly not part of the San Juan Island group, but they're just the islands of the Eastern Salish Sea. And what I show here in that intermediate terrain is there are green rocks and various shades of blue rocks. The blue rocks is a sedimentary overlap succession. It's basically a basin that migrates upward into turbidites. It's really well organized. It's heavily deformed, but it's really well organized stratigraphically. Everything that's shown in green is what we're calling the Vindovi assemblage that used to be called the Fidalgo Ophiolite. And so this is showing our reinterpretation of what the Fidalgo Ophiolite is. So the first 2/3 of what I'm going to show from now on is the geologic evidence that led us to the conclusion that the Fidalgo Ophiolite is a melange derived from an ophiolitic arc but it's a sedimentary rock interbedded with volcanics. So it's accumulated at the Earth's surface. So this is the classic model of Ned Brown, 1979, where he said, look, I recognize a sedimentary succession. I know that the bottom of the sedimentary succession is latest Jurassic, and it sits on top of volcanic plagiogranites, on terms of feldspar porphyries, sheeted dike complex, layered gabbros. There's an unexposed region, and then you run into big blocks or big bodies of peridotite. So he interpreted this, even though he said that there's an unexposed segment, which is underwater, that you go from mantle, the peridotite, to lower crust, all the way up to the sedimentary succession sitting in a relatively intact Ophiolitic sequence. Later work by Brandon et al. Modified this just a little bit. First of all, they said there's a fault contact underneath this thing. It's not a continuous section, so the peridotites are probably disassociated with that structural section. But they bought into the idea that this is relatively intact basement complex overlain by a sedimentary succession. So everybody's on the same page so far. So now what I'm going to do is I'm going to walk through and take a look at some areas. We're going to go, for the folks here in the room, we're first going to go up into this region, Vindovia Island and Cypress Island, to look at some of the lithologies here, and then ultimately we're going to come back down and look around Fidalgo Island. And for those that are in the distance, we're going to start up here, Cypress Island, Vindovia Island, and then come down and look around the various rock successions that are exposed on Fidalgo Island. We had a field trip just a little over a year ago, for the Geological Society of or Pacific Northwest or Northwest Geological Society. That's where I met Ralph. And we had a 2-day field trip. And so this might be something to put into the back of your mind. First day was with boats, and this is the boat we actually chartered. So we can get about 30 people on it. You can drop the plank and you can run out and look at rocks. And then the second day is we had vans on Fidalgo Island. We actually walked through traverses on the inlands of the water and then some of the areas along the beaches so that we could look at the geology. And the objective there was to show the sedimentary succession sitting on top of what we interpret to be a rock. Okay, so let's start looking at some of these constituents. This is an example of a bunch of pillow basalt. You can see the pillows in a basaltic matrix. And so this is a volcanic breccia with pillows. This is located on Vindovia Island, which is way off to the northwest. In addition to these rocks, we find bedded or banded chert deposits interbedded within. These are basalts. These are basalt breccias. So we've got big blocks of chert floating around in a matrix of breccia. Now, if we just go around the corner here to the east or to the right on the slide, we can go to a beach and you can actually see some of the contacts within that sedimentary succession. So these are examples of the sedimentary rocks that we have interbedded within the volcanics. This is a sedimentary breccia. It contains chert, basalt, argillite blocks in a volcaniclastic matrix. And so we've got this big pile of rocks that were originally thought to be sitting there as part of a Ophiolitic succession composed of all of these. So we're going to keep finding these sedimentary successions surrounding individual blocks as we go through this presentation. Next up is we're going to go to the north end of Cypress Island here. Whoops, I didn't get that one. We're going to go to the north end of Cypress Island here to take a look at the Vindovia in this area. So we've mapped out the details of the geology. The dark green are volcanic basalts, and a lot of them are pillowed. The sort of yellowish green, the JV, VB are volcanic breccias. And then there are even areas where we have sedimentary rocks interbedded. And so we've been able to map out the geometry in some detail on the island itself. So first thing you can see is these rocks have enjoyed a lot of strain. They've undergone an enormous amount of deformation. If you just look at these, you can just see that there are foliations. Oops. Wait a minute. Did something here. There we go. You can see the foliations in the rocks. These rocks have really been deformed very extensively. Just to give you an idea, there's vein deposits for both quartz and calcite vein deposits. Some of the veins are folded, some veins is cross-cut the folds, and we can then say that there's multiple generations of vein formation. In some areas, you can find aragonite veins. In others, which suggest that they may be related to a metamorphic aragonite, but you've got to be very careful with aragonite. You've got to demonstrate that the aragonite you're looking at is truly metamorphic, because aragonite veins have been documented in the mid-ocean ridges today. So getting an aragonite vein is great, but it's not enough to say that this is a metamorphic aragonite. Give you an idea, so S naught would be old bedding. This would be here we've subdivided the first deformation into two subclasses. We got S1A and 1B. And you say, well, why would you not just call it 1, 2? Because they're isoclinal. So in other words, the layers become parallel to each other with really high strain. And only in areas where the earlier foliation is folded by an axial planar to the second foliation can you differentiate them. Everywhere else, they're just plain parallel. So everywhere else, well, it's S1. Was it 1A, 1B? I can't tell you. In some places, you could even find up to 1C. So it is an enormously complicated first deformation. As an example of a lithic volcanic sandstone with blocks of argillite floating around in it. More lithic volcanic arcosic sandstones with blocks of basalt. Examples here of pillow basalts, and in many cases you can find radiolarites within the interstices of these pillow basalts. So we've got pillow basalts, we've got sedimentary, volcanic lithic sedimentary rocks, we've got argillites, we've got basalt breccias, basalt pillows, and everything in between, and they're all mixed together. We can map them out, but they're really a very complicated mixture of these different lithologies. Okay, next place we're going to go is down south, and we're going to look at the western shore and the southern shore of Fidalgo Island. And so we get to see some of the constituents of those we're going to go south down through here. These yellow, orange blobs, these are peridotite, and we're going to be looking along this shore and then work along the south shore of the island down through there. So we remapped Fidalgo Island extensively from the published USGS maps. A lot of that work was done by Ned Brown and his students, and Tim and John Wetton from the University of Washington. And what we're able to identify are some major form surfaces. First of all, we were able to identify some large scale structures. Large scale structures. This is the big syncline. There are thrust faults, there are clippa of basement over the top of sedimentary rocks. It's a really complicated pile of rocks. And so by mapping it in detail, we were able to get the macroscopic distribution of the various units. This is on the west shore of Fidalgo Island, and here you can start to see big blocks. The little class in here. This is a sedimentary breccia, and it's composed of things like pieces of gabbro, pieces of basalt, pieces of feldspar porphyry in a sedimentary matrix. And this is a relatively coarse sedimentary matrix. Here's a closer view of the rocks. So you can see Some of these are plagiogranites, some of these are gabbros, and they're all sitting within this lithic matrix. And so we can map out these lithic matrix deposits throughout this outcrops along the shore. That gave us one of the real advantages that we had over Ned Brown, is that we had really good boat coverage. We had a mothership, a big boat that we would anchor, live on, and then we had a 14-foot Boston whaler that we could get into these areas and then get into the beaches. When Ned did his work, he used a canoe. And I can tell you, I wouldn't go out there in a canoe, maybe a kayak, but zero chance for a canoe out there because that's dangerous water and it's really cold. So hats off to Ned, but he didn't get to see a lot of this stuff. And I think that would have changed some of his opinions. Okay, next we're going to go south, and we're going to run along the southern margin here through Deception Pass. And so for the folks on the screen, we're going to come down and we're going to run through here and look at some of the outcrops through Deception Pass area. I'm getting better at this. It's a little, I think I'm going to need a drink after this. Yeah, okay. So here's a great example on the shoreline between Rosario Head and Bowman's Bay. And so we got a big block here of banded chert. This is all a lithic volcanic greywacke. There's a block of basalt. There's another little bit of more chert. And then right here, this is a feldspar porphyry. And so just along the shoreline, you can just see these great big blocks, and some of them aren't terribly large. We find blocks like this, and this is really important. So you can see argillite, you got this great big block, and there's more argillite sitting below it. And so if we look in close at that block, what you discover, that block is composed of a sedimentary breccia, composed of the same things that it's sitting in. So we had a really complicated history where he started cannibalizing the rocks themselves, putting them into big blocks and dumping them back into the melange. So there was this whole cannibalization process. So we've got chert, we've got argillite, we've got plagiogranite, we've got gabbro, I don't think there's no gabbro here, and basalt clast floating around in a breccia that is now a block within the same units. So a very complicated history of deposition. Okay, oh yeah, next place, we're gonna go to Rosario Head, and I think it's right here, and I think this is probably one of the most beautiful examples. You can go up and stand on it, but it's nothing like looking at it from the water. Because if you look at it from the water, then you actually understand what you're standing on when you're up there, and you can't get to it because it's all cliffs. So this is the western part of Rosario Head. This is Rosario Head. This is argillite, it's banded chert. This is basalt, more argillite. Moving a little farther to the east, here's the basalt coming over the top here, more blocks of chert. And so we've got the hardest part in many of these areas is determine whether the basalt or the argillite is the matrix, because they look like they're really mixed up. And remember, they're extremely deformed. So they're not just sitting in their sedimentary environment, they've been deformed in a series of isoclinal folds, so it makes the distribution really complicated. A little bit farther east, this is another great outcrop. This big block is plagiogranite. So it's an orite. And as we go down through here, you start to see, if I annotate this with, this is a plagiogranite olistolith. This is argillite. And here's some more plagiogranite blocks floating around in that argillite. So here the matrix is argillite with a great big piece of plagiogranite floating around it. Now the next stop, probably the best, is Hope Island. It's south of Fidalgo Island. And what Hope Island is, it's a peridotite. And biggest problem we've always had is most of the peridotite are out on Allen, Burroughs, the Washington Head on the western side of Fidalgo Island and Cypress Island, and they may be just one huge mongoose sheet. But here we've got one that's relatively bite-sized, and one of the places that we're going to go on this area, right there on the southeast tip of that island, because it turns out there's some absolutely critical observations you can make there. So this is a simplified geologic map of that little tip. And so what we have is in this orangey pumpkin color is we have peridotite, and if you got dots on it, it's cataclastic serpentinite. And then the red or the pink are diabase dikes, and they're all overlain by a lithic volcanic breccia. So this peridotite and the dikes were at the surface of the earth so that you could put the sedimentary succession on top of it. So we're going to take a look at that. Okay, so here's what cataclastic serpentinite looks like. Now, what's really important here is what originally recognized by Mark Brandon, and we've documented it in spades. He was right on. The earliest deformation these peridotites and a lot of these plutonic rocks experienced were brittle fabrics. They're cataclasites. They were in a fault zone. They were brutally deformed. Now, all of the penetrative fabrics, you know, the D1s and the D2s and all this cleavage development postdates the cataclasite. So cataclasite occurred before the penetrative deformation. So we would argue that the cataclasite is what brought the stuff to the surface. So you could ultimately get it low enough confining pressure to break it up. And then we took the whole thing back down to air, so it's probably down to 10 or 15 kilometer depths. This was sort of our Rosetta Stone. And so what this is a series of diabase dikes, unfortunately barren of zircon, because we dated them, tried to date them 3 times, they're barren, crossing penetratively deformed cataclystic serpentinized peridotite and overlain by a volcanic breccia. Got a dike, SRP, serpentinized peridotite, it's cataclastic, another dike, and more peridotite, it's not serpentinized here, but it's serpentinized here. And sitting on top is the BRX, which is a volcanic clastic succession. It starts off with blocks of peridotite, a little bit of diabase, and as you go up section, it turns into pillow basalt. So there's the cataclastic succession. If you poke around in here, you'll find a couple of spots where you'll find peridotite blocks. Yes, ma'am.
Your pointer for the folks.
No, I'm doing that occasionally.
Okay.
Yeah, no, not as often as I should. Sorry, guys, but whenever I can remember it. So, but these blocks are pillows and they're basalts. So that means that this cataclastically deformed peridotite, mantle rock, was at the surface to get unconformably or non-conformably overlain by a erosional contact that passes up into pillow basalts, and those pillow basalts are Jurassic. So all these constituents had to come to the surface to get buried into sedimentary succession, and then we deform the whole thing. So this is the visualization that we have of more or less what this would look like, and there's no scale for on purpose. The orange things, those are peridotites. How big are they? Yeah, they're like small to the size of anacortes. They can be any size you want. Then we've got pillow basalts floating around. We've got argillite blocks, and we've got sedimentary succession. So what we have is a sedimentary block in matrix melange. The brittle fabric formed prior to penetrative deformation, which is it's associated with deposition. And then following this, the Vindovi understand a major 2 really high so low temperature, high pressure metamorphic events and penetrative deformation. Next part of this story is to look at the blue rocks. Now there's different blue rocks in this thing. I've got what we call the Lummi and what we call the Jeanette. They're age equivalent. They're lithologically very similar. They probably are the same unit, but we're going the route of being splitters, not lumpers, because what we can demonstrate the Jeanette formation on Fidalgo Island is sitting in depositional contact with the Vindovi. Nowhere else on the Lummi formation can you see a depositional contact with anything. It's in structural sheets. And I would argue that the Lummi formation looks like it's got a little higher metamorphic grade and it's probably deformed a little bit more. But, so we're going to look at what these rocks look like. So we're going to focus on the southern part of Fidalgo Island, where we were able to map a very big overturned syncline that all the rocks are dipping off to the west, and we have a stratigraphy in the Jeanette formation that we could actually work out in this area. So this is, oh, I'm back up here. So what I'm going to show is we're going to show a cross section right through here to give you an idea what the structure is. So for the folks out in the hinterland, we're going to run a cross section right through here. So that's what the structure looks like. So it's a recumbent syncline. And so on the west limb, everything's upside down. And as you go down the section to the core of the syncline, then everything starts going right way up until you run into the Vindovi on the other side. So you go from Vindovi into the sedimentary rocks, inverted. Then everything's now right way up, back down into the Vindovi on the other side. What's interesting is the Vindovi that is exposed on opposite sides of the syncline are different. One side's got basalt, the other side's feldspar porphyry. So the lateral continuity of materials in the Vindovi is very restricted. This is the basal contact of the Jeanette formation, and it picks up pieces of whatever it's sitting on. Picks up basalt where it's sitting on basalt. It picks up feldspar porphyry where it sits on feldspar porphyry, and sometimes plagiogranites. This little unit, which is about 10 meters thick, can be traced clear across the island. It's a remarkable marker. It really is. So you can find this basal conglomerate breccia that is the bottom of the sedimentary succession. You go up section, you go from that coarse clastic succession at the basal contact, and you move into argillites. There's black shales here. And then they pass up into silicified jasperoids. And so what we had, so you're going through the lower section is relatively fine, and ultimately this is a fine coarsening upward succession because we run into more and more clastic turbiditic successions throughout this section, which is on the order of about 1 kilometer thick. Now we're looking at a cliff from Canoe Island in Deception Pass, and we're looking back at Fidalgo Island, and the vertical features you see here, that's bedding within that syncline. So we're looking at the end of the syncline. So for the folks, the distance, we're looking at these contacts, which I highlight here, give you a better appreciation for the orientation of bedding. And if you go all the way down to the water, you can find sedimentary structures here. And so you've got this really well-organized sedimentary succession sitting on this garbage dump of all these different things that came from an ophiolitic succession, and it's really well established. So we can actually date these two units. Right at the basal contact at a great rock quarry, and if you go there, it's the rock quarry Lakeside Industries south of Anacortes. Well, it's actually just outside of Anacortes. Go talk to the Billy and say, I want to go look at the contact because he knows exactly what you want. He's got 10,000 geologists go through there. And so he'll take you right to this contact, and you can go to that yellow dot right there, and you can look at radiolaran chert. And Davy Jones dated that chert as the latest part of the Jurassic, and it passes up It sits on top of the breccia, passes up through radial lineature, up into the sedimentary succession, and detrital zircons from that sedimentary succession. The youngest age that we have from those is a youngest zircon of 121 MA, so Cretaceous. So we've gone from the latest part of the Jurassic through the lower part of the Cretaceous, and that's what we have for the Jeannette in terms of its age. So if you look at this, this is a cartoon that we're arguing. This is sort of what this whole succession looked like. First of all, you had the Vindovi with all these bits and pieces in a blocking matrix, and then you park on top of that a sedimentary succession that is really well organized. Now, the last part I wanted to mention, though, is that the most important aspect of this is all of the sedimentary accommodation occurred prior to major penetrative deformation, because it turns out the Jeannette, the sedimentary succession on top, sees the same deformational history as the Vindovi underneath it. So the Vindovi didn't get broken up by deformation. It was a sedimentary deposit, and then everything together got deformed and went deep, probably 10, 15 kilometers, and then came back up. So give you some examples of some of these structures. We're going to look at, this is the Lummi. This is the part of the Jeannette that doesn't have a bottom. So we separated it. Whoops, sorry. So we're going to go up to this area. See if I can get these things synced. There we go. So we're going to look at the sedimentary succession and the structurally overlying Vindovi on a younger thrust fault. So we're going to look at this fault right here, and we're going to look right in this area, which is this area right here, to look at the structures that you see in the Lummi, which is the equivalent to that sedimentary overlap, and the deformed Vindovi sitting above it. That's what the Lummi looks like. That's not bedding. That is cleavage. So that is a penetrative fabric associated with deformation during metamorphism. If you actually go in and look in detail, every once in a while you'll find bedding that comes up and goes into isoclinal folds through here, and this cleavage is axioplanar. So this foliation here, as I'm showing the folks at distance, that's a metamorphic foliation, and occasionally you can actually find closures on sedimentary layering that are isoclinally folded, but they've been isoclinally folded 2 times. So they are really hammered.
So the question from the audience down here, is that a quarry just southwest of Mount Erie?
No, it's not that one. That one's a gravel quarry. No, it's north. It's on Havicost Road. It's in Anacortes, just south of the city limits. It's Lakeside Industries. There's a big controversy about the quarry just south of Mount Erie, about whether they're going to open it or not. Okay, so what we have here is we have the Vindovi, which is the greenish hued rocks, overlying the rocks that look a little more bluish looking. And that's the lower rocks are the Lummi. And so if I annotate this, there's the fault. And that takes the older rocks, putting them on top of the Lummi. So now what we're going to do is we're going to zero in right at the outcrop to show you what one of these structures actually looks like. Okay, stop that one in. There we go. So now pencil for scale. This is the Vindovi, and this is a lithic volcanic breccia. There's the fault contact. This is the highly penetratively deformed and veined Lummi formation. So for people away, up here, this is the volcanic lithic Vindovi fault contact, and these are veins, both calcite and quartz veins of different generations. Now, the main point is that we can show at these outcrops that the first foliation, one, that's the one that's associated with all this metamorphosis, is cut by this fault. So you can see S1 comes up here, it does not pass through, these do not pass through that contact. That gives us a relative timing of when the penetrative foliations and the younger imbrication occurred. So this younger imbrication is post that metamorphic foliation. And here, again, another picture of the fault. Again, between the green and the sort of bluish gray. But what we can show is the second foliation crosses the fault. It's continuous across that structure. And so you truncate the first and you have the second foliation. So we can bracket the movement on this fault as between the first and the second. Now, what do we know about the ages from all that work that we did in the Gulf Islands, Susha, all of those areas, Waldron Island? We know that the second deformation is Paleocene. So that means this thrust fault occurred since the latest part of the mid-Cretaceous and before the Paleocene. And so that we can work out the timing because we've got the fabrics from all these different areas in the region to be able to tie back to these types of structures. Now, first of all, you don't do this type of analysis measuring 10 or 20 foliations. We measure thousands of foliations. I mean, thousands of foliations. I think. Yeah, so what I hope that I was able to demonstrate is the reason we interpreted the Fidalgo ophiolite to be a block and matrix melange. The key points are the block and matrix melange is a sedimentary succession. It was overlain depositionally by a well-organized basinal succession that was turbiditic, that has a thickness probably on the order of about 1 kilometer. Now, determining stratigraphic thicknesses in rocks this deformed is pretty much a exercise in futility. All we can say is some of these outcrops are in excess of 1 kilometer. Maybe this unit was maybe up to 1 kilometer, could have been thinner, but it can't be thicker. Okay. The big boundary then, like Peter Misch said, is separates this whole assemblage, which is coherent. I mean, you can find all these different blocks in all these different islands, but the structure is the same, but the lithologic units are different than when you go across Rosario Straits. And turns out they are different when you run through this fault system that separates this block from the high cascades themselves. And so we've got 3 structural sheets. We've got a history of deformation. And what we've done is find out that the ophiolite isn't an ophiolite, it's an ophiolitic melange. But what we also did for the larger scale problem is we've shown that the continuity of these rocks across that boundary is now broken. And so this is now the potential site of large magnitude lateral displacement at this part of the Cordillera. And I'll stop there. Say again?
Just repeat the question.
What's the sedimentary origin for the block and matrix melange? And that's really a great question. I think what it's related to is when you have displacement along curved boundaries, on plate boundaries, that as the displacement starts migrating around curvatures, what happens in these curvatures is that the terrane or the package of rocks that's sliding along the boundary ends up with different components of strike slip versus dip slip movement of the driving plate. And what happens is those terranes start to extend along strike and they create basins and they create exhumation. Now, a colleague and I from Rice University years ago did a GPS geodetic survey in the Aleutian Islands. And what we were able to demonstrate through the big curvature of the Aleutian Islands using GPS geodesy over a period of about 4 years is that the eastern Aleutian Islands, just west of Kodiak, is moving west parallel to the oblique convergence of the Pacific plate at about 3 millimeters per year. But by the time you get all the way out to Attu, which was invaded by the Japanese, but it used to be a Coast Guard station, so you could still get there. You really change the curvature. That island is moving west at 32 millimeters per year. So you've increased by an order of magnitude this block of rock, because it's curved, and you've got a plate going underneath it, is stretching, and we calculated the stretch at 300%. So now either you can homogeneously stretch it, which I don't think you do, or you can break it up and make really deep basins and start dumping stuff that you're pulling out of depth. And so I think it's related to the migrating terrains along the boundary. You're creating these localized depth centers.
So it's kind of an extensional or.
Yes, you're in a complete convergent boundary, but you're stretching parallel to the boundary, and so you create these local basins and you start dumping things in. And when you create the basins, you're pulling the basement out. And if you pull the basement from, say, an accretionary prism, and you're down at 15 kilometers, and by the time you get to about 5 kilometers, hey, it's low pressure, low temperature, and you're going into cataclastic deformation. And so I think that's when the periddotites get all their fabrics, the cataclastic deformation, because they're being pulled out of the mantle, eroded, flopped right back into this basin where you put basalts on them and you put sedimentary rocks on them.
One question I have is when you go east of that
Right.
old black line,
Right.
you didn't talk that much about what you see there for structures and what makes you think it's.
We're just starting to work. Now you're getting into the terrane phyllite, you're getting into the shuxin, you're getting into this whole.
This is my phone, those are the terms, so you.
Okay, so the question is, what happens to the east of this eastern northwestern boundary? And what we're doing is we're going into the eastern, what is it, metamorphic suite used to be the Darrington phyllite, the Shuxon, and lithologically they're very different. Now we have not worked out the structure in that area, so we don't know what the structure is. I suspect it may be different, but I don't know. I just don't know. The advantage of working in places like the San Juan Islands is one, you get to you've got these unbelievable outcrops. As long as it's between 100% outcrop. It's just phenomenal. Once you get up into the islands, things start to get a little sideways. But once you go up into the Skagit Valley, forget about it. You got to be into like vegetables in a really big way. Yeah, just right. Yeah. The question is, once you start taking something down into an accretionary complex at a convergent plate boundary, how do you get them back up? And that is a really big question. And for years, you would have people like Mark Kloos would say you get return flow and you get all these different diapiric possibilities of trying to get these materials. Once it goes down to 15 kilometers, how do you get it back? Well, the work that my late colleague, Hans Ave Lallemont did in Venezuela, looking at these metamorphic complexes, he documented by going through excruciating detail that everything went down this way, but it all came apart this way. So you've got to think three-dimensionally. And guess what? It's a four-dimensional world, but you got to think in 3D. We always get trapped in subduction by thinking about the convergence. But if you actually have extension parallel to the boundary, those things that went down this way then can come back up in a different direction. And I think that was a paper about 1981. And it's, I think, underappreciated, but it was really a revelation. And he went out to Santa Catalina and found the same fabrics there in the Franciscan. So shortening brings things down, but the extension perpendicular to the shortening brings them back to the surface. But if you think it's a hard thing, taking something down to 15 kilometers and bringing it back, wait till you start dealing with the UHPs, the ultra high pressure rocks that go down to 150 kilometers and somehow get back to the surface. And I've talked to my colleagues who have worked on that, and they said, well, the problem is the structures that bring them from 150 to 15 kilometers are so overprinted by the shallow stuff. We don't know. It's just they went down. We got diamonds and coesite, and now they're sitting at the surface. How'd you do that?
Bye-bye, everybody. See you later.